Welcome to ICHEP2020. Welcome to ICHEP2020.
So, Melissa, please go ahead.
Hello to everybody watching. I'd like to give you all a warm welcome to ICHEP, the International Conference on High Energy Physics, which is the most prestigious conference for particle physicists in the world. This year, the conference is meant to be held in Prague, but for the first time ever, it's been held online and organized by Prague. I am Melissa Yexley. I'm an experimental particle physicist PhD student at the University of Lancaster, which is in the UK. And I'm working on the ATLAS experiment at the Large Hadron Collider at CERN, which is in Switzerland. And I'm very pleased to introduce you to Nobel Prize winner, Professor Barry Barish, who will give you a talk about how we can understand our universe using gravitational waves. Now, just a quick introduction to Barry Barish's life and achievements. Barry grew up near Hollywood. In high school, he played for the tennis team, and each year they used to play against the Van Nuys High School. And he would often play against the same little blonde kid who was named Bobby. And it was only years later, watching an interview on TV, he discovered that this little Bobby was actually Robert Redford, the famous actor. And it was in this time that, despite being particularly proficient in maths at school, Barry didn't have any special interest in maths or science. And this was confirmed when he was often asked what he wanted to be when he grew up, and he would answer novelist. It was only when Barry went to the University of California, Berkeley, that he actually had his first physics course. And this was where he found his love for physics. He then went on to complete a PhD in experimental particle physics, staying with the University of California. Barry then moved to Caltech for a postdoc position and has remained there ever since, leading an incredibly rich and scientific academic life. After spending many years involved in multiple cutting-edge particle physics experiments, Barry moved to a rather different branch of physics, that of astrophysics, which is particularly incredible about this switch, is that not only is this a switch that's quite rarely made, but that it was achieved so successfully. So much so that Barry received a Nobel Prize for decisive contributions to the LIGO detector and the observation of gravitational waves in 2017. And this will be the subject of Barry's talk today. There is a link below me here on YouTube where you can type any questions, and Barry will answer these at the end of his talk. Please do ask away if you have any questions, as it's very likely that someone else is wondering the exact same thing too, so please don't be shy. I will now hand over to Barry for this exciting delve into gravitational waves.
Hi, everyone. I'm Barry Barish. I'm the public speaker for tonight at the ICHEP 2020 meeting. ICHEP is the traditional big meeting for particle physics. It's held every 2 years. It moves around the world, and it's where particle physicists and others that are interested hear about the latest results on large accelerators, the latest theories, the latest ideas, and the new areas that particle physics has an impact. For example, particle physics now is very important in us understanding what the dark matter is in the universe, what the dark energy is in the universe, how the universe began. It's important to us in understanding quantum physics and so forth. So high energy physics has a very broad impact. So far, because it's so infantile, gravitational waves have been not part of the venue, but should be and will be. Gravitational waves, which I'll talk about today, represent understanding, again, one of the fundamental areas of physics, which is the forces. The four forces of nature are the strong interaction that holds us, the nucleus and us together, the weak interaction, which causes radioactive decay, the electromagnetic interaction, which is electricity and magnetism and so forth, and gravity, which we're all familiar with. But gravity is really very, very weak, and we know the least about it. What we've discovered just a few years ago is something that Einstein actually predicted more than 100 years ago, and that is that gravity has waves, just like electromagnetism has waves. And those waves were an important discovery, of course, but they give us a new tool to understand our universe. And that's the theme. I'll tell you a little bit about gravitational waves, but that's the theme that I want to explore with you tonight. So let me explore it first by getting to a full screen and showing you some slides that will that I'll talk from as we go through the lectures. So here we are. Now we're going to try to explore how we can understand more about our universe with gravitational waves. This subject that I'll come to after a little while, we can reflect a little bit first at something that we've all witnessed, but maybe haven't realized so much. That is, what has caused the dramatic advances in astronomy over the recent 50 years, say, during the 20th century and the early 21st century. It's really the fact that astronomy, as invented by Galileo, covered the visible band of wavelengths. We looked through a little lens and we saw four moons of Jupiter, and from that, astronomy was born. In 400 years, we've developed a lot of tools so that we study astronomy now in other wavelengths. We study it in the ultraviolet, the infrared, with gamma rays, with radio waves, and so forth. And most recently, we've made tremendous advances by looking at the same phenomena. Here I just show a picture of a very well-known phenomena, the Great Crab Nebula, looked at in different ways, looked at it in the ultraviolet, looked at it in the radio waves, looked at it in visible X-rays and so forth. And it's the combination of all that that gives us so much insight now into these phenomena in astronomy. And in 20th century, in 21st century in astronomy, we've seen this even go another step, not just multiple wavelengths like I showed, but combining instruments. And all of you probably noticed or saw last year in the newspapers a beautiful picture, a photograph-like picture of a black hole. That was done by looking at instruments in the radio that are in the South Pole in Europe, in the US, in South America, and in Asia, and by all kinds of difficult and wonderful combinations of the data, made it behave like it's one instrument the size of the Earth. And with that, they had the power to image a picture of a black hole. And that was called the Event Horizon Telescope, this thing altogether. And so that is now beyond using different wavelengths, is using different instruments. Event Horizon Telescope was very complicated because of all the instruments, and really did the problem by combining this data in using modern computers on data that wasn't necessarily formatted the same or meant to be put together, but was put together to show this beautiful image of a black hole. The next frontier for astronomy is believed by many people to be a part of the subjects that I'll talk about today, called multi-messenger astronomy. So by multi-messenger, what we mean is not just electromagnetic radiation. Well, it's all electromagnetic radiation if we talk about radio, infrared, ultraviolet, visible. So we just looked at different wavelengths of electromagnetic radiation, but we also could look at other messengers. Those other messengers are ones that have been found in particle physics, neutrinos, and the one that we found, gravitational waves. These come about in very, very different ways. The neutrinos by some sort of nuclear interactions, gravitational waves by the gravitational force and some changes that enable producing gravitational waves. And so from the same phenomena, we can get very, very different messages. And we've got a little start on that, which I'll show you, which is pretty dramatic, even since we discovered gravitational waves. So the idea is you use all the electromagnetic instruments, of which that's the most mature, gravitational waves, which I'll talk about mostly today, and even neutrinos. This is a picture of the neutrino detector detecting neutrinos under the ice, deep under the ice at the South Pole. So let's first try to understand a little bit about what gravitational waves are and then work our way into the science. We all learned gravity from Newton. We learned this famous formula, which he wrote down in the Principia, which is that the force between two massive objects is the product of the two masses divided by the square of the distance apart times a constant that took another 100 years to figure out. And that's the force, and that's universal gravity. It describes why the moon goes around the earth, why the apple falls out of the tree, the tides, and essentially everything to do with gravity as we see it in everyday life from the time 1687 until Einstein came along, with one little exception, which I'll point out. Einstein came along in the year 2000, in the year 1915, and proposed at that point a new theory of gravity. I won't explain the detailed question, but this is the equation, but this is his equivalent of Einstein's equation. And it's his universal gravity, and it's needed for reasons that I'll point out. Universal gravity, in the case of Newton, described the forces between two massive objects and what the formula is. And in Einstein's formulation of gravity, it's not a force at all. It's the fact that space and time are unified and are affected by the presence of masses and the changes of any mass distributions. And that four-dimensional space and time together is what makes the theory rather complicated to understand and to calculate. But out of that, Einstein predicted much about gravity. The only problem that existed at this time where Newton's theory didn't give the right answer, as observations had gone, is the orbit of Mercury around the sun. The orbit of Mercury around the sun is a very elliptical orbit. Each time it goes around, it's affected by the positions of all the planets and moons. And it's moved to an orbit that's a little bit like a daisy petals. And the distance from here to here, or the amount that it bends, can be calculated using Newton's theory. And it doesn't quite give the right answer. It gives an answer that's about 10% less than the actual bending that was observed. So this was the only puzzle that existed at the time Einstein came along. And in fact, it could have well been experimental. It could have been because we don't yet understand where all the planets, moons, and objects are, the massive objects in our solar system. And it could also be that there's an object that might be missing this between Mercury and the sun. In fact, that was a popular theory in the 1800s. There were false discoveries of such a planet in between, but it was never found. And as far as we know today, it doesn't exist. Einstein's theory solves this problem. It gets the right answer. That's the first requirement of a new theory. If it's going to replace or add to a theory that we already have, it first has to maybe solve some problems that the other one couldn't. So Einstein's theory solves the problem of Mercury around the sun. The way it does beyond that is it explains something that Newton didn't explain. Why does the apple fall from the tree? Einstein gave us Newton gave us a formula, but he did not tell us why the two objects are attracted to each other, but rather just a formula for how they are. Einstein's theory tells us why. It's a warpage of space-time. I show it in this picture here on this grid. It's a little bit like a trampoline. If the Earth is sitting on the grid, it warps the shape of space and time. Each of these points are changed in both space and time. And if I put an object out here, it'll roll toward the Earth. And that's basically the reason the apple falls to the Earth. And it's the reason the moon stays attracted to the Earth while it's trying to go around and goes in an orbit around the Earth. So that basically is an explanation that Einstein's theory gave that Newton's theory didn't. Next, it solved a conceptual problem in Newton's theory. Newton's theory, when the apple falls, you understand that the apple fell immediately. There's no time that passes. But if we start talking astronomically, it starts to become a problem. For example, imagine that the sun were to burn out right now. In Newton's theory, you would know it immediately. That's not the case for Einstein's theory or for nature. It takes 8 minutes for light to travel from the sun to us. So it would take 8 minutes for us to see that it's dark. And likewise, the gravitational signal, whatever happens gravitationally, should also travel at the same speed, not instantaneously. So in Einstein's theory, gravity or gravitational waves, it'll be travel at the same speed as the speed of light. So these are the conceptual problems that Einstein solved. And then he made, that's a nice theory, but then it made a new prediction. And that new prediction was that light, not just masses near each other, would bend if they came near a place where the field or the space-time got distorted by a massive object. So imagine that you have light coming from behind the sun, past the sun. The sun is massive, distorts space and time around it, and that bends the light as it comes. That amount of bending he calculated, and he suggested that it can be seen if you look at when the sun is dark, which means a full eclipse of the sun. That experiment was done by Sir Arthur Eddington, and he saw that not only did it bend, but it bent just the amount that Einstein had predicted. And in fact, this bending of light around the sun is what made Einstein worldwide famous. Basically, this is the New York Times article that described the strangeness of light bending, which of course is something that is hard for us to imagine. We think of light going in an absolutely straight line. So beyond that, what happens often in science is what's a new discovery leads to it becoming a new tool. And so in modern astronomy, the fact that the light gets bent as it goes around objects has become a tool called gravitational lensing. If we have a source and it goes by an object that's, say, dark, the light that goes by it gets distorted, it gets bent, the image of the source looks different from that. And by studying the image, one can tell something about this dark body that was sitting here. And that technique has been used a lot in modern astronomy. It's called gravitational lensing. And this is two pictures of lensing around around an object. One up here, and a second one which is famous and can almost be seen with the naked eye, and that's the Einstein cross. Now, let me go on to the new phenomenon, and that's waves that come with gravity, like light waves and electromagnetic waves come from electromagnetism. It turns out that gravitational waves are a necessary consequence of special relativity with its finite speed of information travel. Gravitational waves come from the acceleration of masses and propagate away from them at the speed of light. Let's again reflect on electromagnetism. Electromagnetism comes from taking two sources and oscillating them, a dipole, and it travels at the speed of light. So the difference here is we have to create what's called a quadrupole moment, and that happens when you have two objects going around each other like this, and then the waves go out like gravitational, called gravitational waves. These distortions that I'm showing here are distortions in space-time itself. They don't have something connected with them, as far as we know, like the photon is to electromagnetism. So it's much more like what happens when you throw a pebble into a clear pond. The pebble goes to the bottom, but the rings of water on the surface go out, much like this picture here, and not carrying anything of the object, but a result of the phenomenon that happened when the pebble went in the water. It's likewise here, when the two objects are going around each other, they distort space and time, traveling out at the speed of light. So gravitational waves are ripples in space-time itself. They stretch and compress space-time. The amplitude of the waves that we'll look at are 10 to the minus 21. I emphasize the number being very small. That's 10, 21 zeros point something. So it's a tremendously small number. That's why we live in a world where we don't see big distortions because of gravity, because it happens to be very weak, which is good. But that's a finite number that if we're good enough, we can calculate. It changes the distance between any object by this strain, which comes from gravitational waves or Einstein's equation, where delta L is the strain times L. So if we have an object that, say, a circle of beads, free to move, and a gravitational wave comes through, they would stretch in one direction by a distance delta L, where delta L is this little h, 10 to the minus 21, times L. And that means if it's 1 meter in size, the stretching would be 10 to the minus 21 meters. That's a terribly tiny number. And it explains why when we made a gravitational wave detector, it's kilometers in size instead of meters in size, making this number more like 10 to the minus 18 instead of 10 to the minus 21, which is still a tiny number. It's the size, basically, of a proton. So it's a tremendously small number that we have to measure, and it takes very good measurements to do that. We do it by a principle called interferometry. Now, let me reflect just a minute. If we want to measure something very accurately, it can be very hard. And so we have institutions, big institutions that do it for us. The National Bureau of Standards in the US, and a big agency in Paris is the main one that measures for us and tells us how we determine how much a kilogram is or how long a meter stick is. Those are very difficult to tell. It turns out that it's much easier sometimes to tell the difference between two objects that should be the same or almost the same. And that's the trick that we use. Interferometry measures the difference between light, the time it takes light to go in perpendicular directions, going the same distance. And so if light goes from a laser on the left, it's a mirror. You divide it in two and send it down the two arms. If the two arms are constant, it should come back at exactly the same time. I can invert one compared to the other, and they'll just cancel. And then my sensor that sees the amount of light would see nothing, they just cancel. But if they change, like I've shown here, which is what happens with gravitational waves at a frequency that I'm showing of a couple times a second, then the time it takes to go down one arm is different than the time down the other arm. And what we see is they don't quite cancel here. We see a signal, and that's what we look for. The size of this for us is 4 kilometers. I mentioned that it's big kilometers, which means we have to measure a different distance of a few 10 to the minus 18 meters. In order to do that with an instrument like this, we have to be able to do it to essentially 1 part in 10 to the 12 of the wavelength of the light that we're using in the laser. That's many orders of magnitude better than anyone's ever done in the past, and that took us many years to develop the techniques to do that. The second problem is that I can't measure the distance from here to here if everything's moving anyway, and it turns out the Earth moves too much. So in our case, we have to suspend this interferometer, that's the word suspended here, from the Earth, basically float it, and we have to eliminate any vibrations from the Earth, again, to 1 part in 10 to the 12. And these two problems are what made it so difficult experimentally to develop an instrument that was good enough to measure gravitational waves. We're finally, when we used interferometry, we started building the device that detected gravitational waves in 1994 and detected gravitational waves 21 years later. The two instruments that we have are identical. One's in the Northwest in Hanford, Washington, and the second one is in Louisiana, Livingston, Louisiana. The distance between these two is 3,000 kilometers. That's a time, if light was going from one to the other, of 10 milliseconds. So if I have light coming this way, or a signal coming this way at the speed of light, it would come to the Hanford Observatory 10 milliseconds before it would come to Livingston. Or if I come the opposite direction, it would come to Livingston 10 milliseconds before Hanford. If it came down the middle, it would be at the same time. So we require that the two see the same signal within 10 milliseconds, and the difference in time tells us something about where it came from. And that's basically the technique that's used. These are the two detectors. They're identical technically. These are the long 4-kilometer arms. This is where all the optics and lasers and so forth are, and a 4-kilometer arm this way. This one's identical in Livingston, Louisiana. The terrain is very different. This is swampy forest, and this is high desert. But the instruments are the same, and they basically work the same and give the same sensitivity and result. This is the sensitivity then of a gravitational wave detector. All the lines here are just all the things that limit us. And the region where we can sense something is the colored region up here. This is this little H that we measure. This is 10 to the minus 21 right here. So this is the place where we can see something. All these things limit us. If we look at the highest frequencies, we're limited by how much light we have, the lowest frequencies by the residual shaking of the Earth, and the intermediate frequencies by the fact that we're working at room temperature. So this is basically the area that we look at. And you can notice on the bottom that goes from tens of hertz to thousands of hertz. And that's just like the ear. And it turns out that that's not an accident. We're doing nothing acoustic. So we're not like the ear, but evolution has taught us that if we want to communicate with each other, then we have to do it where the Earth is the quietest, and that's the audio band. And likewise, the Earth is quiet to do something very different than audio, and that's to look for gravitational waves. So it turns out when we're looking on Earth, that's the frequency band we're able to explore. And this is the exploration. You can see our curves look a lot like this. The coordinates are a little bit different. And this is a year-by-year improvement as we made the detector come to the design over a period of 2 generations in 21 years. This is just a picture, and it's the only one I'll show you, of a technical part, which is how did we manage to make it isolated from the Earth in 1 part in 10 to the 12th. In this picture, you'll see that these are springs, and those springs are just like shock absorbers in your car. They take the shock when you go over a bump, and they transfer to lower frequencies where they don't bother you in the car. We do the same thing. If there's something in the audio band, the shock absorbers take it and move it out of the audio band as well as they can. And then all these other little devices in here are the fact that what we learned we had to do even more than that was to actively sense any gravitational, any movement of the Earth with seismometers and then push back and correct for it. So this is a very sophisticated instrument that basically passively gets rid of as much as it can with shock absorbers and then actively gets rid of the rest, or down to 10 to the 1 part and 10 to the 12th, by sensing any remnant movement of the Earth and pushing back against it so that our mirrors that were reflecting the light stay still. This is where we were about halfway between 1994 and when we discovered gravitational waves. We had reached this little line shown here, and in a different configuration, we could go a little bit lower here, but not as well at low frequencies. And so we had reached the design we had done before we added, for example, the active seismic seismic tools to be able to reduce further the seismic noise. At high frequency, we improved the power of the laser. At middle frequencies, we made bigger and better mirrors. And at the lowest frequencies, we basically provided better seismic isolation by doing the active seismic. And lo and behold, the improvement was a factor of 100 on the scale that I showed you at low frequencies. And that was essentially how far out we could look in the universe. We could look 100 times further when we reduced the amplitude that much. And basically a factor of 100 further out in the universe is a factor of 1,000,000 in number of galaxies, stars, and so forth. And so it's not surprising that once we made this big gain, we were able to then detect gravitational waves, even though we had run for years and not seen them before. So this was then in 2015, September 14th, our first observation of gravitational waves. I'll just show you this quickly. What happens when gravitational waves come through? Their waves, so they go up and down. They basically get bigger as the two objects get closer to each other, and then they finally merge. So what we're seeing is the last parts of the merger of what turns out to be two black holes, making this up and down narrower and bigger, and then merging and ringing a little bit afterwards. This is the interferometer in the state of Washington. This is the interferometer in Louisiana. And basically if you add the two together, they fall on top of each other. If you slide one slightly compared to the other, which is telling you what direction it's in. So that was the discovery of gravitational waves. The line below, this is it again, shown on a different graph. And the line here is, the lines here are the calculations coming from Einstein's theory. And you can see that this looks, except for this being a little wigglier because it's just experimental, it looks very much like the curve here. And if you subtract one from the other, you get nothing but just random up and down. So this was the first event ever seen of gravitational waves. From that, we could calculate all kinds of things, and I can't take the time to tell you, but we identified it immediately as two black holes, 136 times the mass of our sun, 129 times the mass of our sun. that adds up to 65, but the final mass of the black hole ends up being 62. So 3 solar masses of energy went off in the form of gravitational waves. And then we can even tell something about the spin, 2/3 of the maximum spin it could be, and how far away it is. That's about 1 million light years. And that was the masses of the 2 objects. So that was the discovery of the first gravitational waves. The second one we saw a few months later, and you'll see it's typical in physics. It's not exactly the same. This has many, many wiggles. And the many wiggles are because they were lighter. The 2 black holes were lighter, and so they stayed in the detector longer before they came to a time to merge. And that was the second event ever seen. Since that time, we saw a whole bunch of them. They were all black holes. Until we saw this one down here, which I'm going to talk about separately, where these are all tenths of a second. This is some different scale, 10, 20, 30, 40, 50, and it stayed in our apparatus much more than a minute. That meant it was a very light object to stay so long in our detecting bands. This shows something about what we learned just from the very first ones. And remember, I was telling you that looking at the sky in different ways, we are bound to learn something more in astronomy. So here we learned quite a few things just from the very first observation. First, that stellar binary black holes exist. That wasn't really established before. That they come in pairs, one going around the other, just like the moon around the Earth. That they merge, that's going to happen in Einstein's equations, but that they merge actually within the lifetime of the universe because we've observed it, and that they're very heavy. This was a huge surprise to astronomers because very heavy stars, this is 20 times the mass of our sun, are very hard to reconcile with how they can be stable. They tend to be unstable, but yet it turns out they exist and they form these black holes that we saw. So once we make these observations, then we have to determine where things are. So now I want to talk about, okay, we make these observations, how do we connect them to electromagnetic observations? In order to do that, we have to be able to find the answer very quickly because we can't go back and tell them to go look at the sky after everything's all gone. So we basically have 3 detectors that search. One's in Italy and 2 in the US. We then very quickly determine what was the difference in time when the signal arrived in these, and that gives us a position on the sky. Then we spend some time, up to about 30 minutes maximum, but mostly much shorter, deciding what it was and whether it was a real event and whether it's worth telling astronomers that might have to turn their telescopes. And we do all that within minutes. And then we spend hours, days, maybe even weeks determining whether the whole thing makes sense by much more detailed calculations. And about 10% of the time, we were wrong in alerting astronomers. We alerted them, but it turns out it was not a good candidate in the final line, but we're pretty good at announcing them. And of course, if they turn their telescopes, we better be pretty good, or they'll get tired of pointing them. This is the early data when only LIGO existed. That's the 2 US detectors. And what we saw were big bands in the sky, about 1,200 square degrees, when we saw some of these gravitational wave events. That wasn't good enough to tell astronomers. It's when a 3rd detector was added in Italy that gave us the ability to determine where something happens in the sky much, much greater. And that happened in 2017, August 14th, 2017. So the detector in Italy came on at that time, and we quickly saw an event where we had gained the position by comparing with the time they saw the event compared to when we saw the event in the US. That was the most accurate that we've ever seen an event. And none of these black hole events ever gave anything that a signal that was observed in any sort of electromagnetic observatory of any type. That's, of course, what you expect. That's why it's called black holes. And so you don't expect to see it except in some other kind of detector like gravitational waves. But then, only a few days after we had the Italian detector on, we saw that the gravitational wave signal was the gravitational wave signal from an event that happened simultaneously basically was the one that I showed you that was very different. We located it very well in the sky. And from that, we basically could tell that it was also observed gamma rays from a satellite called Fermi. And they even came from the same region in the sky. This is the region seen by Fermi. This is the region seen by LIGO. And basically from that, we were able to determine that there were gravitational waves simultaneously with high energy photons. That was quickly put together by looking at all the other wavelengths, looking at neutrinos, looking at visible light, looking at radio waves, looking at gamma rays, turning telescopes, roughly half of them in the world, to look at this region of the sky. And with that, signals were observed at different times in different frequency bands, but coming from the same source. All of this, when it was put together, satisfied a theoretical conjecture that what was being observed was called a kilonova. A kilonova is when two neutron stars merge together instead of two black holes merge together. And that picture is what gave us the picture of a kilonova. Then these many measurements were looked at technically to compare with the different wavelengths, the different times, the amplitudes, the different colors, and everything agreed with the kilonova. This is a picture of the frequency distribution as a function of brightness, where it's brightest at the different frequencies. And again, it fits this kilonova emission. An interesting fact in that is that we as physicists have always had trouble describing why it is that in the Earth, we have mines and go find heavy elements. Of course, the one we care about the most is gold or platinum that we use in rings, but all the very heavy elements. They're not explainable by what we understand about the sun, because the sun burns by what's called a fusion process. The fusion process starts by burning hydrogen, then helium, then heavier elements. Eventually, as it burns up its fuel, it gets up to iron. Then fusion doesn't work anymore. At that point, only gravity is strong and the fusion dies and the star collapses. And that's called a supernova, and it makes a big bright light, which is observed. So that basically doesn't easily make heavy elements, although we've made arguments that maybe it does. It turns out that you can ask, how do we know all these elements in the lab? In the chart here, and it's because we know how to make them in the lab. We can take a heavy element, iron or something, and bombard it with neutrons, and we make heavier ones. And basically, that's the trick that's always been used to make heavy elements. Neutrons bombarding a target. Sounds a little bit like neutron stars. So in our case, we have the ability then to make something like platinum, gold, maybe from the kind of collisions that we observed. And in fact, in the kilonova picture, the neutron star mergers are incredible factories to make gold. So for example, the LIGO observed neutron star merger, the one that we saw, actually in calculations produced 100 Earth masses of gold. Of course, they're not in the Earth, they're out there, but neutron stars that collided in the distant past produced the gold that then ended up in the Earth. So this now is our best explanation of neutron, of where gold comes from. Now we continue to improve LIGO. We started a data run almost a year ago, and we recorded 56 events in a little less than maybe 45 weeks. We had to turn off this spring because of the COVID-19 problem. But at that point, we had 56 new events. We're off now, and we'll be off for the next year, making further improvements. And an even higher rate, we should be able to see one event a week. So far, from this larger data sample, we're looking at exceptional events. So here's two examples. One is that we've seen more events like the neutron stars, which should be in a band of about 2.75 mass total, some distance around that. All our events fit in that except one. It's about 5 sigma away. We don't know yet why or whether it's something else. So that's one event. We have another one where we have a heavy black hole and a small object going around it. And the small object that's going around it, almost 10 times smaller than the black hole, turns out to have a mass of about 2.5 solar masses. That's the area too heavy to be a neutron star, supposedly, and too light to be a black hole, because it wouldn't make a black hole, it wouldn't have strong enough gravity. And so what are we seeing in between? That's basically for the next talk when I come back, but that's what we're showing now, just the exceptional events based on one event. They might be telling us something. Now let me talk about the future for just a few minutes and then I'll end. We soon will have 5 different major detectors around the world. We're building a third one in India, and the Japanese are turning one on in the Kamioka mine where they do neutrino physics. And so there'll be 5. With 5 detectors, we'll go from today, where these little stripes are how well we can see where something came from around the globe today, and what it will look like by the mid-2020s. So we'll be able to point very well in the sky to alert astronomers anywhere an event comes from by 2024 or so. We also, by having more events, can look for other phenomena. So far, everything I talked about was an in-spiral event. But I mentioned supernova. We can see supernova with gravity because they'll give gravitational waves. We can study spinning neutron stars, and maybe even signals from the early universe. So we have a rich history as we improve. We'll do that by incrementally improving LIGO and Virgo in Europe. And within the next decade or so, we know already how to make the next detector. This is an example of a design for the next detector done in Europe, which would be underground instead of where it is now. Longer arms, like 10 kilometers, the shape of a triangle instead of an L shape, be cooled, which makes the noise much less, and have special configurations for low frequency and high frequency. Such detectors will enable us to see much further out in the universe, which means much earlier in time. By seeing earlier in time, we basically start to be able to do cosmology or early universe physics with gravitational waves. I'll mention that in a minute. That's us on the Earth. There's also an experiment which will be in space in the early 2030s called LISA, and it looks at a different frequency band. So now thinking about electromagnetic frequencies for astronomy, we want to do that also with gravitational waves, look at a different frequency bands and different detectors. LISA will give us 10 to the minus 1 to 10 to the minus 4 hertz. We were 10 hertz to 10,000 hertz. And there's another technique of looking at pulsar timing, which is looking at existing pulsars and distortions in their timing. They can give even lower frequency. All of this points to a very rich future. This is just a picture of what will be done in space in LISA, 3 arms in a triangle, 2.5 million kilometers separated. This is the pulsar timing array as it'll be done. And altogether, we'll be able to cover in the future, eventually, a broad range of frequencies, very much like I pointed out in the very first slide in electromagnetism. This is the different instruments that might be able to do that in the coming decades. And this is the different science as you go to different frequency bands. The most challenging and maybe the most interesting is to get to the very early one. And the reason that's so interesting is that gravitational waves are probably unique in being able to give us the information that we need to really understand what the Big Bang is, what the early physics is that gave the beginning of the universe. We now study it using photons. Photons only send us back to actually 300,000 years after the Big Bang. The universe was opaque before that, so we couldn't see. Neutrinos would go earlier, but they don't appear to be experimentally possible because the neutrinos are so low in energy. Gravitational waves go to the very, very first instance because they're not absorbed at all. So if we can detect gravitational waves from the early universe, we can learn how the universe began, how it evolved in the very, very earliest times. And that may be the most profound question we have in physics. So I'm basically finished. I've shown you the birth of what I think is a new astronomy. That's an astronomy with gravitational waves, 400 years after Galileo, on the shoulders of people like Einstein. And I hope you've enjoyed it, and I'll answer questions in a few minutes. Bye-bye.
Thank you very much, Barry. That was a thoroughly fascinating talk, and it was really interesting to see how we can use gravitational waves, just like how we've used electromagnetic waves before, and how we can use both of these messages together to understand the universe and where it comes from. Okay, so let's have a look at the questions. So first up, do you have any hints from theory as to what these exceptional events could be?
That's a good question. So far, the answer is no, but maybe theory isn't quite right. For example, it's very difficult to determine what the lowest mass is that you actually have the ability to be a black hole. In order to be a black hole, by definition, you have to be able to let nothing escape. That's why it's black, which means even light. So light has to bend enough that it doesn't escape. The calculations aren't trivial to do that. So it's been estimated that it's about 3 or 3.5 times heavier than our sun to be able to have a strong enough gravitational field to be a black hole. But maybe that's not right. We're not sure. And again, on the other side, the next lighter object is called a neutron star, something I talked about. And you can imagine that the science of a neutron star is even less understood. We don't really understand the dynamics of neutron stars very well, but we expect they're about 1.5 times the mass of our sun. So that it's in a region where the simple pictures that we have don't fit, often the way physics is done. Whether it requires something radically new, like a new object, or maybe a different understanding of the objects we have, I think is kind of the next step. We need more data, of course, to really be able to tell what we have and what the distributions are like. Luckily, we're going to be able to do that because for one thing I didn't emphasize in the talk is that we're nowhere near limited by nature in studying gravitational waves. It's one of the beauties of the subject, which means that as we can learn how to improve technologies, we should be able, limited by ourselves, not by nature, to be able to make more and more sensitive devices to detect gravitational waves so that we're not as primitive as we are today and being able to explore that science.
It'll certainly be very exciting to see where it goes, and especially because just after you switched on and then you saw something so quickly, it's just moving very fast, and it's certainly very exciting. So the next question, this seems quite a popular one. How can gravitational waves help us to understand dark matter?
Well, let me answer that in 2 different ways. That's a nice question because you picked a question about a subject that none of us understand very well. Dark matter is almost a defense. We find that we can't explain why objects, heavy objects, like in the spiral galaxies, move around at the speeds they do. It isn't explained by gravitational pull or gravity on a bigger scale, like the universe acts like it needs more, that there's more gravity than we see. So we assign it to something we call dark matter. There's two possible completely different explanations. One is that maybe our understanding of gravity is just really not right. Maybe Einstein's equations aren't quite right. There was something in them that he called the gravitational constant, for example. And so it's possible that we need to change our picture of gravity, and that it isn't just some missing matter, but a missing understanding of the whole picture. Of course, gravitational waves are one of our primary tools to understand and test Einstein's theory. So that's the first one. The second is that it could be that we can detect dark matter objects if some fraction of them came from the beginning, meaning what we call primordial dark matter, maybe even these black holes. So we don't know yet whether these black holes came from big stars that just eventually collapsed and made black holes, or maybe some of them came actually in the Big Bang itself, what we call primordial black holes. If that's the case, the primordial ones can explain some fraction of the dark matter. So we're not as direct or good as these dedicated dark matter experiments that we're all looking forward to what they'll be able to do in the next decade, at least answer for us what our best candidates are. But if we don't see those, then we have other possible ways that we have to be able to explain in nature what's there. And maybe it's a change in the theory, and maybe we can give some clues about that. Or maybe it's actually some of it's primordial. So touch the subject, but not as well as maybe these be.
It'll certainly be interesting to see it as a different tool to all of the dark matter experiments.
Yeah.
That'll be very interesting to see. And so in your talk, you said that as far as we know, there's no associated particle to the gravitational waves, as there is how we see the photon for electromagnetic waves. And as a particle physicist, do you think the graviton is likely to exist, or do you think it's just a different form of physics? And
you know, I think of myself more as a scientist than as a particle physicist that has to assign particles to everything.
Yes.
The graviton is a very tempting object, and first thing I should say is it's absolutely not there in Einstein's theory of gravity. It's a classical theory. There are no objects, so it's not like it's there, but we haven't seen it yet. However, we know that Einstein's theory of gravity is not the whole story, as we also know that quantum field theory that explains everything that happens at CERN pretty well is not the whole theory. And in fact, somehow it's crazy that we have two theories of physics that are separate. We need one theory of physics. So we don't have the whole picture in either quantum field theory to explain what happens at CERN, or in classical general relativity that Einstein brought forward. So people have worked for years to try to, tens of years, 50 years or so, even Einstein part of the time, in trying to find a unified theory. It's one of the big goals of physics, and one that we need eventually, is to find a theory of physics that describes everything. A unified theory may well have some form, some quantum form in gravity as well, which would be something like gravitons. But since we don't have a theory, we don't know really what to look for. So we look for the most primitive thing, which we've done. So what's the most primitive thing? It's like particle physics. So they're little particles that are something that's going like photons are in electromagnetic waves that are accompanying gravitational waves. So how can we look for those? I showed those waves. They go up and down, and they've come from 100 million light years or a billion light years away. If they have a massive object, even light mass object that accompanies them, they're not going to go at the velocity of light. they're going to be somewhat less than the velocity of light. That introduces the technical term we use, dispersion in the up and down things that I showed. And so we test for that. Do those wiggles that we show when we have many events, and a lot of them to look for, agree with zero mass, or that there's some mass causing it to disperse some and come at a slightly different shape? We see no evidence for a dispersion, which means no evidence for a graviton that you ascribe some mass to that would lead to a dispersion. And in fact, we've set a limit that's incredibly small. I won't give you the number because it's just throwing around numbers, but incredibly small for the mass of a kind of classical graviton that you take as a picture like from particle physics over and just assign it and see what it would do to these waveforms. But as I said, that's a kind of naive way to look for it, and we haven't seen that, but we didn't probably expect it very much. And yet we have a need for something that's going to bring together these two sciences, something like a quantum particle. A graviton would be a strong way to somehow tie these subjects together.
Okay, thank you. That was a very interesting answer. So moving on to more of the detector side, for the initial discovery, Virgo was your biggest competitor, and I'm wondering how and why you think you made this discovery before them.
Oh, that's a sociological question. We both proposed to do gravitational waves, or were funded to do gravitational waves within a year of each other. We were funded in 1994. I think they were funded slightly before us, but maybe started building comparable time. And interestingly, we've obviously been in competition. It was a big goal to see gravitational waves, and we were in competition, but we also, from a very early date, had a much closer collaboration than Atlas and CMS that you work on. And the reason is that there's a big gain. There's a gain other than confirmation in which we understood very early in having more than two detectors. I showed that in our ability to point. So very early, since I'm talking kind of personal sociology, we agreed with people in Virgo to collaborate enough to, for example, have in detail the same format for our data. That means that we, without a big learning exercise, can analyze data from Virgo, or they can analyze data from us. We formed enough of a collaborative venture between us so then in 2007, I think, about 8 years before the actual detection, we started exchanging data. Even though the data wasn't seeing gravitational waves, so we could analyze each other's data. We have separate collaborations like Atlas and CMS, but we have also kind of a collaboration of collaborations, that we call it, a way that we look at putting all of it together. Why were we faster? I would say, without kind of bragging or something, we had a little more foresight. At the very beginning, we convinced the NSF of two things. One, and this was at the very beginning, 1994. One was to spend a little bit extra, not so little, but on the facility itself in order to make it flexible enough that anything we envisioned in terms of improvements, we would be able to put in without having to rebuild the facilities themselves. And usually in these big detectors, the facilities are a big part of the expense and time. So if you look at a picture of LIGO, I don't have one here, of course, and you see these big vacuum tanks, they have ports all over them. We don't use all those ports. But what we did is make something where we'd have access in any way we wanted so that we could put almost anything we dreamt inside, because that's our laboratory inside them. So the second thing we did with NSF is to ask them boldly for money to develop the second generation detector while we were building the first generation detector. And so that we could use all the expertise we had, the people as they finished building the first one, the best designers could keep working, rather than what often happens is an experiment's built, they take data, then they enter into a design and build the second generation. So I don't know exactly what happened in Virgo, but the reason we were so speedy, if anyone can call 21 years speedy, is that we envisioned a facility that did, in fact, not have to be modified in a major way, that we built from the beginning, and that we started R&D, for example, on the active seismic isolation in the 1990s. We started learning how to do that.
So talking about upgrades as well, you mentioned that you're going to use cryogenics to cool
Right.
upgrade.
Right.
What kind of temperatures are you going to go down to? Is it similar to that we use at the Hadron Collider, or
Yeah. So this question is a good one because it illustrates that experimental physicists don't always know what they're doing. So what we know is that there's a big gain to be made in cooling. As you know, anything that is at room temperature, things move around and all kinds of things happen. So we need to cool, want to cool. And you can ask why we didn't cool even from the beginning. It's really a hard problem, and it's harder than the problem at CERN, and I'll explain why. It's harder because there's more unknowns, not necessarily technically. There's more unknowns. The first thing is technically, though. We have to make sure that we cool without disturbing this incredibly sensitive instrument. So we can't shake anything at the level of 1 part in 10 to the 12th. So you can't cool by pumping, or you have to cool in ways that basically maintain the sensitivity of the instrument. So that's a technical challenge. But the second is the unknowns. We don't know. You started the question by asking me what temperature. And I would say the Japanese have jumped in and they're building one, but they've picked basically to go to very low temperature. At very low temperature, they use sapphire for their material. That's not necessarily optimal. And so what we've been doing is working now with people who don't usually work in this area, but we've brought into the collaboration material scientists to find the right material to which at the temperature we work at will be extremely quiet thermally. So basically all materials aren't the same that way. And so that's the first requirement. And the one that presently looks the most promising is silicon, crystalline silicon. So not fused silica, but crystalline silicon, single crystal that you grow because it's then a very stable thing. But even if you do that, what is its properties at the temperature? So it's maybe 70 degrees instead of very cold. And lastly, how can you coat it so that it's reflective? And that's a material science problem. And reflective coating on LIGO itself, we use fused silica mirrors on LIGO, and we have 20 layers of a dielectric coating. And one of the limitations in LIGO is the interface between this dielectric coating and the fused silica. It's an interface problem. And so there's a material science question in doing this optics and mirrors and finding the right temperature. And we now have a pretty interesting, I think, R&D program with a whole bunch of universities and material scientists to develop what the right one is. We've got a few years because we expect to go cryogenic, maybe the end of the coming decade.
That sounds interesting. It'd be interesting to follow all of these material science investigations into it. It's a completely new, different area. So. Then you mentioned that because you are so sensitive and you obviously can't pump in the gas, and that's not as easy as it is, say, as at CERN. There's been a few questions about people asking about the background signals and maybe could you describe more in depth, like what are the background noises coming from the Earth?
The background, we don't have background. There's first a big difference. The backgrounds at CERN, when you look for whatever you're doing on your thesis, are physics backgrounds. And so you have these big simulation routines which have been built up by the experience of what we know about collisions over the years. And then you look for a little bump like the Higgs on top of this that takes years to build up. Our backgrounds are not physics. They're not gravitational wave physics. So our backgrounds are nature. And they are, and that's why we're in a situation where, because they're nature, they're beatable. If we can eliminate something in nature like thermal noise or shaking of the earth, we're just limited by how well we can isolate from that. Well, if you have a background that's physics, you have to live with it, which is your case at CERN, for example. So for us, we have three major backgrounds. At the lowest I mentioned them, but I'll mention them now. At the lowest frequencies, the problem is that the Earth shakes too much. And this is a very steep function. It falls as frequency to the fourth power. And our ears learned that, and they cut off, and we don't go to low frequencies because the Earth is really noisy at low frequencies, and it drops very rapidly. And that we use, as I said, seismic isolation, which is a combination of shock absorbers and actively sensing movement and fixing it. That we can do much better, but that's what it is at by low frequencies, I mean tens of hertz. And that's the frequencies where we detected the black hole collision. So it was the most important, and it's the why I showed it in the lecture. In the middle frequencies, kind of where the sensitivity is the best, we're limited by just KT, thermal noise, just the fact that molecules move around in our mirrors, and there's room temperature, and that's why we'd like to cool. And again, it's just a technical problem, cooling. We'd be much better off cool, but we have to learn how to do it. And we're not good enough yet to do it, but we will do it, I'm sure, in the next 5 to 10 years. And at the highest frequencies, we're limited by, just like our ears, you're limited when you go to high frequencies and hearing very high voices or high violins or something, because you have to sample faster and faster, and you don't have enough sound to hear it in your sensitivity in your ears. In our case, we don't have enough photons. So as you make it smaller and smaller at high frequencies, we need more and more photons, which means to do better at high frequencies, we need to have more light, which is higher power lasers, and better trapping of the light and focusing of the light in the apparatus itself. Again, it's just a technical question. We've done pretty well to get to where we are, but we're not limited by anything fundamental. So we can foresee how to do all this, not tomorrow, but over a period of the next couple decades, I'd say.
That'll be interesting to see. So I just want to move over to perhaps something more personal questions. There's a lot of younger people asking and saying that they're really interested in gravitational waves and even quantum theory. And they're wondering if you had any advice as to how to get into physics and how to work at places like LIGO and CERN.
There's a lot of programs for young people to get into CERN or LIGO. I'm familiar with both, and and it's much better than years ago. I think young people can actually get involved in research at a much younger time in a natural way than in the past. Certainly, maybe for high school kids, it's local what's done. So I'm mostly familiar with what's done around here, and most universities in the US have programs where college science students and young scientists go out in the community and go to the high schools, and there's various ways that they try to bring them into research. There's very much more programs for college students at a time when it was very hard for me at my age when I started to get involved in research as an undergraduate. And the opportunities to do that, of course, exist in almost any research university, if you happen to be in a research university, but even students who go to, say, a liberal arts university. There's very good summer programs at CERN in the US at various laboratories. In LIGO, we have some large number of summer students who work with young researchers like you. They have projects over the summer, and it's competitive, of course, but there's a lot of opportunities to do that. There's also good opportunities to go visit these labs. I think CERN has a very extensive outreach activity where people can come and see a lot of things. And US laboratories similarly, including LIGO, we have outreach centers in LIGO. We're much smaller, we're just an experiment, but we have a lot of outreach to the local communities, and including the local schools and so forth. So I think there's a lot of activities. I recommend very strongly, having been through a career in physics, that if you want to do science, whether it ends up being physics or engineering, don't do it all by book learning. Get yourself connected to something where people are doing science or engineering as early as you can, by doing it during summer, after school, whatever it is. The sooner you do it, the better.
I can agree with that, especially from the coding side of it, because we do a lot of coding in the particle physics side. And I think if you've got your hands stuck in, that's the best way to learn and see how to use it, rather than just reading word by word through a book. Hey, let's see what other questions we have. We've got, it might be a bit early to say this just so recently after the discovery, but do you think, can you foresee any useful applications of gravitational waves for technology?
Let me answer that question in a way. It's a question I get asked. Of course, if you make a great discovery and you win a Nobel Prize or something, it's one of the first things that mostly reporters ask you, what's this good for? And my answer is that's not quite the right question. I'm going to answer by saying I don't know for gravitational waves first. It's a very weak thing. I can't imagine, but who knows? But let me answer the question a little bit more broadly, because it makes a point. And that is doing fundamental research, where we are doing curiosity-driven research, whether it's looking for the Higgs boson or looking for gravitational waves or whatever the problem is. What we're often asked what the value is of that, other than developing technologies, developing young minds, developing our curiosity and so forth. And one thing that is true is that historically, doing fundamental curiosity-driven research has paid back society probably more than incrementally driven research. For all of us, probably we would be better off in handling this pandemic if there was more basic research being done on pandemics rather than incremental work developing vaccines and so forth. I'm not as much an expert on that as the physical sciences, but it is true that probably the reason we live as long as we do now, the primary reason was the discovery of penicillin, which was not done by incrementally research. It was basically serendipitous and done by people driving their curiosity. Penicillin, which was important. In physics, some of the most, fundamental discoveries have led to tremendous impacts on society. The first one, I'll name two. The first one, and as long as we're near Einstein. So the first one, and these are two that were near me in my career. So I didn't do them, but I was there and didn't know anything either. One was in Berkeley. And so in Berkeley in the 1960s, when I was a young scientist, there was the discovery, which won a Nobel Prize, a set of discoveries that were basically proving a theory of Einstein's called stimulated emission. And this was something he proposed in 30 years before. So ours was a little longer than 30 years, but they did that. I remember it being a great discovery. It came in first in steps. Nobody had any idea that that was useful for anything, just like your question to me. At the time, the Nobel Prize was awarded for stimulated emission. It's now one of the biggest industries we have. It's the laser. So the laser was only discovered maybe a decade that it was useful to have this stimulated emission focused light, a way to focus light in a very nice beam, which has turned out to be crucial for everything from eye surgery to us having pointers when we talk, or everything else that lasers are used for today, something like a $20 billion a year industry. The second, these just happen to be ones I was near, so I'm just picking them because of your question. I was working for a while as a particle physicist at Cornell on their electrons machine, doing decays of tau leptons. And down the hall from me was a laboratory where people were actually discovering another principle of fundamental principle, which they discovered, called nuclear magnetic resonance. And that was a shared Nobel Prize with one of the persons being the one at Cornell who was working in a lab when I was there. And again, nobody had any idea that that was useful for anything. It's not a huge financial thing like the laser, but it's rather important because it's now the basis of the most valuable imaging tool we have in medicine, which is the so-called MRI, magnetic resonance imaging. Of course, they changed the name because people don't want to get into a machine that has the word nuclear in it. So the word nuclear magnetic resonance is buried, but magnetic resonance imaging is nuclear magnetic resonance. And so that discovery, fundamental discovery, so that each one isn't going to lead to something. And that's why I say it's the wrong question. But doing fundamental research where we make breakthroughs fundamentally, some fraction of those historically have made a big impact on society. And I think that we shouldn't expect that each one will, or that even we have any vision that they will at the time we do it, because we're really just trying to understand nature. But historically, and I've just given two examples of my own, not my own, but were near me, of the value of basically fundamental research. In terms of gravitational waves themselves, it's so weak that it's hard for me to imagine that it has any practical impact, but I don't have just having lived through others not knowing what their impact is, I really don't know, but I don't foresee anything.
Yeah, I can imagine, like you said, that even in the previous examples, that there's no way you could predict how all of these things are useful. It's that's crazy to be able to so I think we've got time for one more question, and this is probably another one that you get asked quite a lot, but I still think it's quite interesting. So can you describe how you felt when you saw the signals for gravitational waves? Were you dubious or were you excited?
Well, first, if you wouldn't get the same reaction from all my colleagues. So mine's individual. Maybe it says something about me. I don't know. First, I live in California, and our two labs are in Louisiana and in the state of Washington. And because of the fact that we have worked so hard to be able to give an instantaneous response for astronomers, we do see something quickly. But in general, it's not so different from looking at data at CERN, where it takes a lot of work to get to see signals and know what they are and so forth. But we've worked much harder than an alert that you might do on a Higgs when it came through or something. So we basically have an alert system. Of course, we had seen nothing when we were turning on. But when it goes off, there's various emails that come and so forth. This event happened at 5 in the morning in Louisiana, and that was 3 in the morning in California. So I was asleep. When I got up in the morning, I have a sickness that maybe you have too, or I don't know, some people have, which I'll admit to, which is that I actually read my email before I eat my breakfast, which is kind of embarrassing to say, but I do. And so that morning I got up and read my email as I was, coming to. And there were a string of emails, maybe 5 or so, that there was some sort of thing that happened. That wasn't the first time, so I didn't jump in my seat or anything. And then they kept coming, and which was unusual. And as I looked at it, we had a possible event, and after about 2 or 3 hours and talking to people and having some phone meetings, it was clear it was something we had to take very seriously. And I'd say the reactions of colleagues varied from eureka on one end to panic on the other end. And I was panic. So my reaction was totally panicked. And why was that? It was really for 2 reasons. One is that I asked myself 2 questions that weren't so simple to answer. And that is, how are we fooling ourselves? And the second one is, how are we being fooled? They're different, and it took us a month to answer both of them. So once we had meetings, we basically, people asked me how we kept this quiet for so long. It's partially for these reasons, that it takes work to know whether you're right, and you don't want to embarrass yourself when you're wrong. The first one is, how are we fooling ourselves? Came down to the fact that we had rebuilt this detector, put in this active seismic isolation and other things in it. It was a rather new detector. We had turned it on and done tests, but we were just starting on a real data run. So how do we know with a fancy special instrument that it doesn't hiccup and do things at the level of this 10 to the minus 21 that look a little bit like a signal or too much like a signal? And we didn't have experience. And to get the right experience, you have to just run the apparatus and take data for a while. And in fact, it took us a month. So we kept the apparatus running for the next month, monitoring, what kinds of random signals it just made by itself. And of course, there weren't any. But at that moment, I wasn't sure. So that's how we could be fooling ourselves. How are we being fooled? Was the question of, is it possible that some devious graduate student or graduate students actually have embedded a fake event inside of our data somehow? And would that be possible? And I couldn't immediately eliminate that, even though we were careful. Because in fact, the first person that actually identified this event was in Germany at Max Planck Society in Hanover, where we have a lab, an Italian postdoc. And he saw the event. He's the one that called the control rooms. And so the data was, we get the data and then it goes around the world. So it's not, so somewhere along the way, can somebody just embed an event in this data that then looks like a real event? That again was reason for my panic. And we had to actually trace the signal. We have it it's recorded in various ways in the hardware and in recording devices, but we weren't just set up to do this because we didn't expect to find this event like that, but we had to trace it back to the apparatus itself, where we actually could see the signal originated in both the separate apparatuses themselves. We had to go back that far because in principle, although we don't let anybody into the two control rooms, and they'd have to somehow generate events within microseconds of each other in coincidence in the two sites, so it would take a conspiracy, probably not an individual, but nevertheless, we had to prove all that. So my reaction was panic. A month later, I felt a lot better.
I think my reaction would have been panic too, and just worry that something like that had happened.
Yeah.
Okay, so I think it's time that we should wrap up now. Thank you very, very much for taking the time out to give us such an interesting talk and answering all of these insightful questions.
Thank you, Melissa.
Thank you. Thank you everyone else for listening. There are many other public events lined up this week, so please just Google ICHEP2020 to find the public programme and you can join in. There's even some interactive things. And thank you again, Barry.
Okay, bye everyone. Bye, Melissa.
Bye.
Bye-bye.